So far, we discussed many different types of aldol condensation reactions. So we discussed intramolecular aldol condensations, we looked at the Covenangle condensation, the Claisen-Schmidt condensation, and other crossed aldol condensations, as well as the Michael reaction. Now, all these different types of reactions, all these different types of aldol condensations can sometimes take place in combination with respect to one another, that is, right after the other. For example, one combination could be the Michael reaction takes place first, followed by a regular aldol condensation, and followed by a dehydration. Now, when our aldol condensation reactions take place in combination, this greatly complicates the determination of the reaction mechanism. So simply put, it becomes very difficult to determine what the reaction mechanism is in aldol combination reactions. So basically, a scientist, a chemist by the name of Ronald Madgett came up with a rule. He came up with some advice that became known as Madgett's second rule. Now, this is less of a rule and more of advice, because a rule implies that this always works. Now, this doesn't always work, of course, but it works most of the time, and so we use it very often. Madgett's second rule basically states that when determining the reaction mechanism of aldol condensations in combination, always try the Michael reaction first, followed by the aldol condensation, and see if that gives you the product that we want. So, to see how we can apply Madgett's second rule and to solve our problem, let's suppose we have the following reactant and this product, and we are told that we want to determine what the reaction mechanism is of this reaction. This is known as the Robinson annulation. And basically, we know that this is an aldol condensation in combination reaction. So let's apply Madgett's second rule. So Madgett's second rule states that first we have to try the Michael reaction, followed by the aldol condensation and the subsequent dehydration reaction. So let's begin with reaction number one, in which we have our reactant, which is this ketone shown on that side of the board. And basically, in the Michael reaction, this acts as a nucleophile, and it will attack some type of carbonyl molecule. So the first step is to form our nucleophile. Basically, we have some type of base, let's say this hydroxide, present in our solution that essentially deprotonates the alpha hydrogen found on this molecule to create it, or to convert it into a good nucleophile. So we have a resonance stabilized structure that is formed. Now, to help us see things a bit more clearly, let's rotate this molecule and place our bond, this bond right here. So these are our two electrons, and we have resonance stabilization, in which we have this second possible resonance stabilized structure. So we have a pi bond that is formed between these two bonds here. We have a negative charge here, a negative charge here. Now we also form a water molecule, because when the hydroxide combines with this hydrogen, we form the water. So we have water somewhere above floating around. Now, the next step is this anion acts as a nucleophile and attacks some type of carbonyl molecule. This is the Michael reaction. Now, the question is, what type of carbonyl molecule should we actually use? Well, basically, we want to go from a single 6-member ring to 2 6-member rings. And notice that here we have 6 C atoms, 6 carbon atoms, and here we have 1, 2, 3, 4 additional carbon atoms. Altogether, we have 10 carbon atoms. So that means to go from 6 to 10, we need 4 more carbon atoms, and so this carbonyl better have 4 carbon atoms. Now, this isn't a carbonyl, this isn't a simple carbonyl. In the Michael reaction, this has to be the alpha beta unsaturated carbonyl. And that basically means we have to have a pi bond between the alpha and the beta carbon. And in this Michael reaction, this lone pair of electron acts as a nucleophile attacking the beta position, displacing these 2 electrons onto our alpha carbon. So the molecule that we form basically looks something like this. So we have the bond, this is our carbon-oxygen bond, and so we form a bond between this carbon here and this carbon here, and this is our bond right here. Now, of course, we have our 1, 2, 3, so we have 1, 2, 3, 4. So this is our other carbon-oxygen bond, and this is our CH3 group right over here. And of course, when these 2 pi electrons go into this carbon, our 2 lone electrons end up on this carbon here, and so we have a negative charge here. And of course, this negative charge will be delocalized onto this oxygen, but we're not going to draw that in this diagram to basically save some space. Now, in the next step, we want to basically protonate this carbon. So in here we formed our water. This is our water, and now this water can act to basically protonate this molecule here, this carbon here. So we protonated and we reform our hydroxide base, and we also form the following molecule as shown. So we have our double bond between the carbon oxygen. We have this molecule here that now has been protonated. We have our double bond here, and we have this CH3 group here. So we have 2 H atoms and 1 H atom here. Now, in the next step, we basically want to undergo our aldol condensation. So this was our Michael reaction. And according to Magid's second rule, when we're trying to find the reaction mechanism of these aldol condensation in combination reactions, we try the Michael reaction first, and then we try our aldol condensation. So in the second step, to attempt the aldol condensation, we take our base because we're under basic conditions, and we deprotonate the alpha hydrogen of this carbonyl here. So we basically form the following intermediate that now has been deprotonated. So we have this molecule here, and we have a CH2 that has our lone pair of electrons on this carbon, and once again, this is resonance stabilized between this oxygen and this carbon, but we're not going to draw that to save some space. Okay, in the next step, also we produce water in the process. So we have a water molecule that is produced in the process. We're going to need that water molecule in just a moment. In the next step, we have these 2 electrons basically protonate, or actually not protonate, they nucleophilically attack this carbonyl position of our carbon, and we form that second 6-membered ring. And we also displace the pi bond of this oxygen onto this oxygen here. So we form our 2 rings here. This is the bond that is formed in this step, and we have our oxygen with double bonded to this carbon here. We have our bond formed here, and we have our oxygen atom that has a negative charge right over here. In the next step, we have the water molecule that was formed in this step, and the water molecule here basically acts to protonate this oxygen here. And so this oxygen grabs our H atom, displacing this bond, forming our hydroxide as well as this molecule here, which is starting to look like the molecule that we want in the first place. So this looks like our aldol. So this is in fact our aldol because this is our alpha carbon, our beta carbon, and to the beta carbon we have the hydroxide group. So this is our aldol. So this is Michael's reaction, this is the aldol reaction, and the final step to actually form this, we have to undergo the dehydration reaction. In the dehydration reaction, because we are under basic conditions, we have this hydroxide base that basically acts as a Lewis base. It grabs away this alpha H atom because we want to form a bond here. So we grab away this H atom, we form a water molecule, and we also place a lone pair of electrons onto this carbon here. So the next molecule that we form looks something like this. So let's draw the two rings. We have our OH group here. We have our two lone pairs of electrons. Our lone pair of electrons, we have a negative charge here. We also form our hydroxide because when or not hydroxide, we form the water molecule because when this is protonated, it forms our water molecule. In the next step, in the final step, we have these lone pair of electrons basically act to form a bond between this carbon, and that kicks off this hydroxide group under high temperatures, and we form a double bond between those two carbons. And this basically concludes our reaction mechanism because we formed the molecule that we were looking to form in the first place, and of course, we regenerate our catalytic base. Okay, so we can see that when trying to determine the reaction mechanisms of aldol condensations in combination that take place in combination, in this case, it's the Michael reaction followed by the aldol condensation, it really helps to first try the Michael reaction first, followed by the aldol condensation. Although Magid's second rule isn't exactly a rule in the sense that it doesn't always work, it's very useful advice, and most of the time it will actually work. And trying the Michael mechanism, the Michael reaction first followed by the aldol condensation is a very useful technique in determining what the reaction mechanism is of our aldol condensation reactions that take place in combination with respect to one another.